So to wrap up chapter 3, we're going to talk about how these trig functions and their derivatives are related to physics. When trig and physics meet, that's called harmonic motion. Harmonic motion is when there is repeated motion over and over and over, and the motion is the same, but it repeats a cycle. So the most common harmonic motion, well, we see it in the world all around us. We see the tides. The tides follow harmonic motion because they just ebb and flow in and out, in and out. The moon follows harmonic motion because it waxes and wanes as it either grows through its phases or then wanes through its phases. One of the more common ones you probably did in a physics class at one point would be a spring lab, right? Did you ever attach a mass to the bottom of a spring and then do any calculations with that? No. You have to talk to Mr. Edlin. Okay, maybe AP Physics will do it. But right, okay, if you just, assuming that I can drop it straight. All right, so this is harmonic motion. Okay, what is creating the harmonic motion? Gravity pulls it down. What pulls it back up? Okay, the tension of the spring itself, the coil, is strong enough to counteract gravity for a little while, and then gravity takes over. So it's like gravity, not gravity, gravity defying gravity, gravity defying gravity. Okay, it's that physics. This is called harmonic motion as well. And as this spring moves through its cycle of harmonic motion, it has both velocity and acceleration. All right, tell me when it has negative velocity. Now. All right, that's negative velocity. All right, when is it at rest? At the bottom and at the top, okay, twice. When does it reach its greatest speed? Right in the middle, okay? Right in the middle. Okay, it reaches its greatest speed. Why not at the bottom? It's slowing down, right? As it's coming to its bottom, it's slowing down to the point where it's zero. Okay? All right, so my poor Slinky over the years has gotten so stretched I can't stack it anymore. Oh well. All right. Okay, so the example we're going to look at is harmonic motion formed by y equals 5 cos t. Five is the amplitude, which means this spring is going to create motion that goes up 5 and down 5 and up 5 and down 5 and up 5 and down 5. Okay, and it'll do that infinitely in its harmonic motion. And we're going to define time as being greater than 0. And then we're just going to go through the physics of what's going on here as it relates to calculus. All right, so part A, define velocity, speed, acceleration, and jerk. All right, so jerk is the third derivative. Jerk is the feeling you have when the rate of the acceleration is changing at a very great speed. When that rate of an acceleration changes, you experience what we know as jerk, whether you've ridden a roller coaster or whether you've slammed on your brakes. Because your rate of acceleration is changing so drastically, you feel it, and that's what we call jerk. Sometimes jerk is small and you don't feel it at all, and other times jerk is big, depending on how quickly that rate is changing. All right, so define velocity. We know how to do that. We're just going to work our way through. Somebody give me velocity quickly for this question. -5 sine t. All right, so that's our velocity. All right, so then our speed. How would we define that? Okay, not just 5 sine t, that's not going to work. Okay, it's got to be the absolute value. So you could do 5 times the absolute value of the sine of t. So 5 would always be positive, that's fine, but you have to keep absolute values around sine because sine wobbles between positive and negative values. So you can either have the 5 inside or outside, it doesn't matter, but you do definitely have to have the times of sine inside your absolute value.
5 is inside, should you put a negative in front of it?
Doesn't matter. All right, acceleration. Who's got that one? Negative 5 cosines, just the next derivative after that. Okay, we know that the derivative of a sine is cosine, and then negative 5 is your coefficient. And then we work on jerk, which is the derivative of that, okay, which is going to be the third derivative. And when I take the derivative, I'm going to have negative 5 times negative sine, which will work together to be 5 sine t. All right, so as long as you understand the definitions of those things, then you can answer some of the questions that relate to it in a physical sense. So question B. Yeah?
We also have to mention how t is greater than or equal to 0
For each of them? No, that carries on from the beginning. We should probably define, though, our units for each of these. So if we have defined this measured perhaps in centimeters, and time is greater than 0 seconds, then our velocity is going to have units on it as well. Our velocity would be centimeters per second, so would speed. Our acceleration is going to be centimeters per second squared, and jerk is going to be measured in centimeters per second cubed. All right, so answering the question of when is the spring at rest? Okay, if the spring is forming the harmonic motion, when is the spring at rest? Well, the definition of being at rest is having what value for your velocity? 0. So you start with what you just defined your velocity as, and I defined my velocity as negative 5 sine t, and I'm going to set that equal to 0. I don't need a calculator to solve this. Divide both sides by negative 5. And so t is the inverse sine of 0, which is going to happen multiple times. But the first time this is going to happen is going to be at 1 pi. And it's going to happen again at 2 pi. It's going to happen at 3 pi, etc. So the summary of that is that t is going to be equal to k pi as long as k is greater than or equal to I guess we could say it's at rest at the very beginning, so we could start at 0. And it's an integer. So just a basic understanding of the physics as it relates then back to the values of calculus. All right, between each moment of rest, describe the motion of the spring, or describe the spring's motion. One good way to think of this, I'm going to show you kind of a strategy. So between each moment of rest, well, my moments of rest start at 0 and then go up to 1 pi. And then the next one would go between 1 pi time and 2 pi. And then from 2 pi to 3 pi, etc. There's just that pattern of between the moments of rest. And so if I'm just describing the spring's motion, I want to know what is the velocity between each of those intervals. So sometimes we set up a chart like this, and we're asking ourselves what the values of the velocity are. So within the interval, you pick a time that is contained in that interval. So from 0 to 1 pi, an easy one to pick would be pi halves, pi fourths, 3 pi fourths, pi sixths, 5 pi sixths, anything, pi thirds, 2 pi thirds, any time value that's contained in that interval, and you check the velocity. So if I picked a simple one like 1/2 pi, and I checked the velocity there, which is negative 5 sine of 1/2 pi, I get a value of negative 5, because the sine of 1/2 pi is 1. In fact, no matter what value I would have picked in that interval, the velocity is going to turn out to be negative. And so the velocity within that interval is always going to be negative. And so a lot of times what we'll do is we'll just say the velocity is always negative. But it only takes one to check what it's going to be. For the next interval, between 0 and 2 pi, we might pick another value, like 3 pi over 2. If I check 3 pi over 2, if I pick the value of 3 pi over 2, and I put it into the velocity, which is negative 5 times the value of 3 pi over 2, that's negative 5 times negative 1, which is positive 5. That's a positive number. And that means in that interval, no matter what time value you pick, you will also always get a positive number. And so to simplify that, we would say that this interval, produces always positive velocity. And then the same thing would be true in the next interval. When you would check something between 2 pi and 3 pi, you're always going to be negative. And that pattern, because it's harmonic, is going to repeat itself. So patterns from starting with an, how could we summarize that? Starting with an even number, starting with an even number and ending with an odd. So starting with 0 and ending with 1, or starting with 2 and ending with 3, or starting with 4 and ending with 5. Something that starts with an even number and ends with an odd pi will always be what? Negative. And something that starts with an odd and ends with an even is always going to be positive. And so we summarize that like this. Okay, something, you can write it in words or you can write it in symbols. Even pi to odd pi intervals will always have negative velocity. And if they have a negative velocity, they're always going down. Okay, so it means the spring is going down in that interval. So here's a good way to write it. If you want to show even to odd, even is 2k pi, odd is 2k plus 1 pi. An even number can always be expressed as 2k, because no matter what k is, it would always produce an even number. And an odd number would always be 2k plus 1. So even pi to odd pi intervals will always have negative velocity, which means the speed always goes down. Conversely, the spring goes up on the opposite. Okay, it's going to go up within odd to even. So 2k plus 1 pi, and then ending with 2k pi. And so in those intervals, you'll have positive velocity instead of negative. So you have to understand what the question of at rest means. You need to be able to answer the question of what happens between the moments of rest. And then this is sort of the last type of question that you need to be able to answer. So let me see. D. I can try. There we go. Okay. And then the final question, when is the speed greatest? Well, from a physics standpoint, you need to know what happens here. Just like I asked, when is it at rest? You need to know that that means that that's when the velocity is 0. When you're asking when the speed is greatest, it means it's not going to ever get any faster than that moment. At that moment, it's achieved its greatest speed. So what's 0 there? If you've gotten to the point where you're going as fast as you're going to go,
Acceleration.
acceleration is 0. It's like hitting cruise control on your car. When you get up to the speed and you want that to be your max speed, you hit cruise control. And that freezes your acceleration. And your acceleration is no longer changing. Your acceleration is now 0, which is going to keep you at your maximum speed, ideally. Okay, so speed is greatest at the moment, at the instant when acceleration is 0. And so you have to understand that from a physics standpoint. So speed is greatest at the instant we achieve 0 velocity. I think I just spelled achieve wrong. I before E except after C.
Zero acceleration.
Oh, right. I said it. I said the word acceleration and I wrote the word velocity. When you have that understanding of the physical, then you can do the math. And you go, okay, well, I defined acceleration already. I defined acceleration as -5 cos t. So I'll set that equal to 0. Divide by -5, so cos t is 0. So t is the inverse cosine of 0. And that happens pretty frequently as well, but it happens for the first time at half pi. Then it happens again at 3 pi over 2. And it happens again at 5 pi over 2. And so the way to summarize when this is happening is what is true about the numerator. The numerator will always be what kind of number? Odd. The numerator will always be odd. And the denominator will always be 2. And there will always be a pi. And so the numerator will always be odd. That's 2k plus 1. The denominator will always be 2. And there will always be a pi on there as well, as long as time remains greater than or equal to 0. So those are how often the speed will be the greatest at those moments, over and over and over again, on the way up and on the way down and on the way up and on the way down.